Okay, welcome back to part 2 of our lesson on the properties of logarithms. In the previous lesson, we were working on expanding logarithms into a single logarithm into the sum or difference of logarithms. Now we're going to actually work in the opposite direction. We're going to go ahead and try to take logarithms and condense them back under a single logarithm, which becomes very useful in evaluating and then going ahead and solving equations. So let's take a look at number 8. If we look at number 8, do you see an exponent that may have fallen? See this 4 that's out front of my logarithm? That 4 was actually an exponent on this argument of y. So now, remember I told you in this lesson, we're going to be going back and forth. Our brains are going to be working in forwards and reverse. So I'm going to go ahead and put that argument back up top. Remember, I'm taking care of those exponents first, just like PEMDAS tells me to do. So I have log base 10 of x minus log base 10 of y to the fourth. Okay, now remember, as long as your bases are the same and you have two logarithms, those two logarithms with the same bases, and they're subtracted, you can go ahead and condense them under one logarithm where you divide the arguments. So you have log base 10 of x divided by y to the fourth. Okay, and since we don't know the values of x and y at this point, there's not much else we can do with that. We went ahead and condensed it into a single expression, but we can't simplify it because we don't know x and y. Okay, applying the same technique to number 9, we're going to go ahead and condense the two logarithms, but since we don't have variables here, in the end we're actually going to be able to evaluate the expression. So once again, do you see an argument that fell? I'm sorry, an exponent that fell. And if you look right here, this 2 was an exponent that had fallen down. So we're going to go ahead and put that exponent back up top. So we're going to have the log base 3 of 6 squared minus the log base 3 of 4. Okay, and at this point you can evaluate 6 squared or just know that it's 36. Whoops, scroll down, sorry about that. So we have the log base 3 of 4. Now, since we have two logarithms that are subtracted, we're going to bring them under one logarithm. So log base 3. And then we're going to go ahead and divide the arguments. So it's the first argument, 6 squared, divided by the second, which is 4. Now we have some numbers we can go ahead and work out. We have log base 3, and 6 squared is 36. So we have log base 3 of 36 over 4, which is 9. I don't know where this stuff came from on my screen. There we go. So we have log base 3 of 9. And changing that to an exponential, setting it equal to x, means 3 squared. I'm sorry, I'm already giving you the answer. it means 3 to the x power equals 9. So x, sorry about that again, it's a little touchy, x equals 2. So the value of this expression here is x equals 2. The value of this expression is equal to 2. Okay, so scrolling over, we'll take a look now at number 10. And what I would like for you to actually do is pause the video and try number 10 yourself. You see that the logarithms are added. So when you see that they're added, you're going to condense them under one logarithm where the arguments are multiplied, and then go ahead and evaluate the expression. Okay, so there, I hope you paused the video and you got the correct answer. Log base 4 of 8 times 2, which would mean log base 4 of 16. And then we go ahead and turn it into an exponential. 4 to the x equals 16. Therefore, x must equal 2. Okay? All right, now we're going to actually see where this is the most useful, these properties of logarithms, in solving logarithmic equations. So I'll scroll down here to our last section of this lesson, and it's actually solving equations. There's a couple of things that you have to keep in mind before you solve these equations. The first thing you must know, by definition of logarithm, the bases and the arguments can never be negative, or they cannot, nor can they be 0. So in other words, the argument must always be greater than 0, which means it must be positive. So in beginning to solve these equations, what we have to do is we have to make sure that we can condense both sides of the logarithm into a single log. So we're going to apply all those properties that we just learned. This side is already a single logarithm. And it's really interesting to look to see that we don't know the base. But as we work through the problem, I'll assure you that that is not necessary in this particular problem to know the base. Okay, I'm going to go ahead, remembering the PEMDAS, and put this exponent that fell back up here. So I have log base z of x equals log base z of 9 to the 3/2 power, that exponent goes back on top of the argument, plus log base z of 2. Okay. Now at this point, you can either continue condensing your logarithms, or you can evaluate 9 to the 3/2. So I have log base z of x equals log base z, and then 9 to the 3/2. Remembering the bottom number is your root, and the top number is your exponent. Okay, the bottom number is your root, the top number is your exponent. Means I have the square root of 9, which is 3, and then you take that 3 and you raise it to the 3rd power to get 27. Now, continuing my condensing of the logarithms, I see on this right side of the equation, I have two logarithms that are added. So I'm going to go ahead and condense them under one logarithm, where I go ahead and multiply the argument. So equals log base z. Oops. Let's fix that up. Log base z of 27 times 2. Now at this point, if you remember correctly, when we did exponentials, we made the bases the same. And once the bases were the same, we said, okay, once the bases are the same, for the two sides of the equation to be equivalent, the exponents had to be the same. Same thing here. Now that I've condensed it to a log on both sides, once these logs have the same bases and I have a single logarithm on both sides, I can then just say, well, for these two sides of the equations to equal, my arguments must equal each other. So x must equal 27 times 2, or 54. And then, like I said, double check. Make sure, go back to your original problem and see where your x's are. As long as your answer does not make that argument negative, your answer will be good. So if 54 does not make that argument negative, therefore I can keep my answer. So x equals 54. Okay, let's go now and scroll over here to number 12. We're going to apply many of the same principles we were before. We're going to go ahead and condense the logarithms on the left side of the equation this time. I have two logarithms that are subtracted. By using the property of logarithms, I'm going to go ahead and condense those two logarithms into a single logarithm. So log base a. And then I'm going to go ahead and divide the arguments because they were subtracted. 3x plus 5 divided by x minus 5 equals log base a of 8. And I didn't mention it previously on the previous problem, which I said I was going to do. Because I get to kind of drop the logarithm from both sides, it doesn't matter whether I have log base a or log base 10 or log base 40. As long as the bases are the same, they essentially are not needed in the calculations of the answer. So again, now that I've condensed this into a single logarithm on either side, I can now just take my arguments here and here and set those equal to each other. So I can say 3x plus 5 over, that's a straight line, x minus 5 equals 8. And now there's several ways to solve this equation. In these types of instances, I prefer cross multiplication. I just put the 8 over 1 and I cross multiply. So I have 8 times x minus 5 equals 3x plus 5 times 1. And then I go ahead and distribute the 8. So I have 8x minus 40 equals 3x plus 5. Whoops, sorry, scroll down again. 3x plus 5. Solving my equation, subtracting 3x from both sides, adding 40 to both sides. I get 5x equals 45, so x equals 9. Okay, and once again, double check. Go back to your arguments and say, okay, if I plug 9 into that argument, does it make it negative or 0? No. If I plug 9 into that argument, does it make it negative or 0? And the answer is no. So I can at least know that x equals 9 is an appropriate answer. Okay, just a couple more and we'll be finished. So let's go ahead and scroll over and take a look at number 13. Okay, if you notice number 13, there's no log on this side of the equation, is there? There's no logarithm here. Well, we have to deal with this one in a slightly different way. But we're going to start out the same by at least condensing the logarithms on the left side. So this becomes log base 3 of 6 times x plus 2. And they're multiplied because my logarithms were added. I go ahead and multiply the arguments. Okay? Now, you cannot drop the logarithm here because there is not a log on both sides. But if you remember back to the beginning, how do we solve logarithmic equations? We turn them into exponential equations using our flip technique. 3 to the third power equals 6x plus 2. 3 to the third power equals 6 times the quantity x plus 2. And you have a very simple equation to solve. You get 27 equals 6x plus 12, because I have to distribute the x. Let's erase that mark I made. (6x plus 12). Subtracting the 12 from both sides, I would get 15 equals 6x. Dividing both sides by 6, come over here, x equals 15 over 6. And as always, reduce our fractions. 15 over 6 reduces to 5 over 2. And once again, double check to make sure that by plugging 5 over 2 in for x, it does not make your argument negative or 0. And it does not. So we'll feel comfortable then going ahead and saying 5 halves is our answer. Okay, last problem. Okay, we're going to go ahead. Once again, we see that we have two logarithms over here that are added, so we're going to condense them under one logarithm where we go ahead and multiply the arguments. So it's x times x minus 6 equals, come back here, okay, equals 2. And again, I don't have a logarithm on both sides of my equation, so what I have to do then is turn this equation into this logarithmic equation into an exponential. So I have 3, that's an ugly 3, to the second power equals x times x minus 6. So what I get is 9 equals, and I'm going to go ahead and distribute my x squared minus 6x. Noticing now I have a quadratic, and quadratics must be set equal to 0 to solve them. I'm going to go ahead and subtract the 9 from both sides. And then I need to go ahead and factor it. And once again, I believe I wrote the problem down wrong. Okay, sorry for the little bit of confusion here. Little bit of confusion, I'm really sorry. Please cross out this 2 should have been a 3 to start out with the problem. Really sorry about that, guys. And then this should have been a 3, which makes this 3 to the 3rd power. So let's go ahead and do a little erasing here. Three to the 3rd, which makes this 27. See, I make the same mistakes in video that I do in class. And then I would have to subtract the 27 over to the other side to make this minus 27. Great. Now I can go ahead and factor it. You can use the x factor, or no, you need two numbers that multiply to negative 27 and add to 6 would be x minus 9x plus 3. So setting each one of those equal to 0, my solutions are 9 and 3. I get two solutions. Okay, but remember to check your solutions. Okay, think about what happens when I would plug 3 right in there. Wouldn't that be 3 minus 6? Wouldn't that make that negative 3? It would make that argument negative 3. Therefore, 3 is one of what we call our extraneous solutions. It's an invalid solution. 9 is okay. 9 works. So I'm going to circle x equals 9 as my only solution. Okay, thanks a lot, guys. I'll see you in class for your questions.